Good day, everyone. My name is Raymart A. Balmaceda, and I would like to present to you my report for Week 5 of our course, EMG256, Risk Analysis and Management. The topic given to me is about the availability as a measure of performance for repairable hardware items under performance assessment, data, and modeling. So let's start with the definition. We define reliability as the probability that a hazard barrier or its components will perform its required function without failure over a given time interval or mission. The notion of availability is related to repairable items only. Availability differs from reliability in that it considers renewal in terms of repair and maintenance. As such, availability is the probability that a repairable item will function at time t as it is supposed to when called upon to do so. Since it is possible that the item may be under maintenance, such as under preventive maintenance and not necessarily failed, but non-functional, availability is a broad measure of performance. There are several representations of availability. The most common ones are: number one, instantaneous or point availability of a repairable item at time t. A of t is the probability that the item or hazard barrier is functioning up at time t. Number two, limiting availability, or A, is defined as the following limit of instantaneous availability A of t, wherein A is equal to the limit of A of t as t approaches infinity. Number three, average availability, or A bar, is defined for a fixed time interval t as A bar is equal to 1 over t integral from 0 to t A of t dt. And number four, the respective limiting average availability is defined as A1 bar is equal to the limit of 1 over t as t approaches infinity integral from 0 to t A of t dt, as shown on equation 4.25. So it should be noted that the limiting average availability has narrow applications. We elaborate on these definitions of availability in the next slides. If a hazard barrier or item is non-repairable, its availability coincides with its reliability function, R of t, wherein A of t is equal to R of t, equal to the equation as shown in equation 4.26, where lambda t is the failure hazard rate function. The unavailability, Q of t, is obviously related to A of t, as Q of t is equal to 1 minus A of t. So from the modeling point of view, repairable barriers, or here hardware items, can be divided into the following two groups. One, repairable hardware items for which failure is immediately detected or revealed faults. And two, repairable hardware items for which failure is detected upon inspection, or sometimes referred to as periodically inspected or tested items. Next, we go to 4.4.1, instantaneous or point availability. For the first group of hardware items, it can be shown that by using a Markov process representing two states of down and up, the probability that the item remain in each of these states are availability A of t and unavailability Q of t, respectively. The following system of ordinary differential equations represents this Markov process. So the derivative of A of t is equal to negative lambda t A of t plus mu of t times Q of t. And the derivative of Q of t is equal to the lambda of t multiplied by A of t minus mu of t multiplied by Q of t, where transition rates between the two states are ROCOF lambda t and the rate of occurrence repair of maintenance mu of t. In this case, examples of the mathematical forms of lambda t and mu of t are those of 4.12 and 4.17. For the simple case where no trend in the ROCOF and rate of occurrence of repair exists, solving 4.28 yield to the equation 4.29. Note that in 4.29, mu is equal to 1 over tau, where tau is the average time required to repair or maintain the hardware systems. Sometimes, tau is referred to as the mean time to repair or MTTR. Clearly, MTBF or mean time to failure is equal to 1 over lambda in this case. For simplicity, the pointwise availability function can be represented in an approximate form. This simplifies availability calculations significantly. For example, for a periodically tested or inspected item, if the maintenance, repair, and test durations are very short compared with the length of operation time and the maintenance, repair, and tests are assumed perfect, one can neglect their contributions to unavailability of the system. This can be shown using Taylor expansion of the unavailability equation. In this case, for each interval t, the availability and unavailability functions are A of t is approximately equal to 1 minus lambda t, wherein and Q of t is approximately equal to lambda t. The plot of unavailability as a function of time using the equation 4.3 will take a shape similar to that in figure 4.4. Clearly, if the test and repair durations are long, they affect the availability, and one must include their contribution to the item's performance. Vesely et al. Have used the approximate pointwise unavailability functions for this purpose. The functions and their plot are shown in figure 4.5. The average values of the approximate unavailability functions shown in figure 4.4 and figure 4.5 are presented in table 4.2. It should be noted that due to imperfect test and repair activities, it is possible that a residual unavailability Q of O would remain following a test and repair. Thus, unlike the unavailability function shown in figure 4.4, the unavailability function in figure 4.5 exhibits a residual unavailability Q of O due to these random imperfections. If the operation and maintenance is disregarding, then Q of O becomes time independent. Similarly, f of r, lambda, tau of r, and tau of t will be time independent. Figure 4.4 shows approximate pointwise unavailability for a periodically tested item. The equation representing the pointwise unavailability of periodically tested or inspected items when there is no trend in ROCOF and rate of occurrence of repair or maintenance is obtained from equation 4.31, where tau of t is the length of test, preventive maintenance, or both, and tau of r is equal to the length of repair or corrective maintenance, given the test reveals a failure or fault. Next, we go to 4.4.2, limiting point availability. It is easy to see that some of the pointwise availability equations discussed in section 4.4.1 has limiting values. For example, in equation 4.29 has the following limiting value as a is equal to the limit of a of t as t approaches infinity is equal to the mu over lambda plus mu, or it is equivalent to A is equal to MTBF over MTTR plus MTBF. Equation 4.32 is also referred 2 as the asymptomatic availability of a repairable system with a constant ROCOF. So just to be clear, MTTF stands for mean time to failure and MTTR stands for mean time to repair. So table 4.2 shows the average availability functions of hardware items. In this table, we have the type of item or hazard barrier such as non-repairable, repairable revealed fault, and repairable periodically tested or assuming no residual unavailability. We can get their average unavailability by using the formulas shown on table 4.2. Figure 4.5 shows point-wise unavailability for a periodically tested item, including test and repair and repair including test and repair out gauges, wherein uh, T T stands for test interval, TR average repair time, H, and TT or average test duration, H, and F of R, frequency of repair, and Q of O, residual unavailability. Now, we go to 4.4.3, limiting point availability. According to its definition, average availability is a point measure of availability over a period of time t. For non-inspected items, t can take on any value, preferably it should be about the length of the mission, which is the item is supposed to work. For tested or inspected items, T is normally the interval of time between the two successive inspections or tests if we assume that lambda T is very small over the period T. So it is shown on equation 4.33 wherein Q is equal to lambda T over 2 and A is equal to 1 over t integral of 0 to t 1 minus lambda t dt, which is also equal to 1 minus lambda t over 2. Vesely have discussed the average unavailability for various types of systems. Table 4.4.2 shows these functions. Equations in table 4.2 can also be applied to periodically tested standby equipment, with lambda representing the standby or demand, ROCOF, and the mission length or operating time replaced by the time between two steps. So here we have an example. Example 4.5. For a periodically inspected and repairable hazard barrier, assume no trends in ROCOF and no residual unavailability. The following data apply. Lambda is equal to 1 times 10 to the negative 4 over H. T of O is equal to 1 month. So these are the given. T of T is equal to 2H. F of R is equal to 0.1 per inspection. And tau R is equal to 20H. So determine the unavailability of the barrier. Using the equation 4.31 that we discussed earlier with Q of O is equal to 0, we have the formula. T is equal to T of 0 plus tau of T plus F of R multiplied by tau of R. So by substituting the values given, we will get 724 as the value of T. After getting the value of T, we will substitute it on the equation to get the value of Q bar, where Q bar is equal to Q of O plus 1/2 lambda T of 0 plus F of R multiplied by tau of R over T plus tau of T over T. So by substituting all the values, we will obtain 0.0 0.04194 as the value of Q bar. So again, this example represents the point-wise unavailability of periodically tested or inspected items when there is no trend in ROCOF and rate of occurrence of repair or maintenance. And that is the end of my report. Thank you for listening and have a good day.